Welcome to Cloud Wizard. In this video, we are doing a complete deep dive into Typeahead and Autocomplete, the system that powers real-time search suggestions across Google, YouTube, Amazon, and Twitter. When you type a single letter and instantly see ranked completions, there is a highly engineered distributed system making that happen in under 100 milliseconds. We will cover the Trie data structure, prefix ranking, edge caching, personalization, and every trade-off that comes up in a senior system design interview. Let's get into it. Welcome to Cloud Wizard. In this video, we are doing a complete deep dive into Typeahead and Autocomplete, the system that powers real-time search suggestions across Google, YouTube, Amazon, Twitter, and virtually every major product you use every day. When you type a single letter into a search box and instantly see a ranked list of completions, there is a highly engineered distributed system working behind the scenes to make that happen in under 100 milliseconds. We will walk through the functional requirements, non-functional requirements, high-level and low-level architecture, the Trie data structure, ranking algorithms, caching strategies, personalization, and every trade-off that comes up in a senior system design interview. Whether you are preparing for a FAANG interview or building search infrastructure at scale, this one is for you. Let's get into it. Here is the core problem. A user opens a search bar and starts typing. With every single keystroke, they expect to see a fresh, relevant, ranked list of completions within milliseconds. That sounds simple on the surface, but consider the true scale. Google processes over 8 billion searches per day. At peak, there are hundreds of thousands of autocomplete requests per second, each needing to query billions of index terms, apply personalization, rank results by multiple signals, and return a response in under 100 milliseconds end-to-end. The naive approach, querying a database on every keystroke, collapses immediately under this load. You need a purpose-built system that precomputes prefix indexes, serves suggestions from memory, caches aggressively, handles tail latency, degrades gracefully, and updates in near real time as trending queries emerge. That is the Typeahead design problem. Let's walk through the functional requirements. First, the system must return the top K autocomplete suggestions, typically 5 to 10, for any prefix a user types within 100 milliseconds of the keystroke. Second, suggestions must be ranked by relevance, combining global query frequency, recency or trending boost, and personal search history. Third, the suggestion index must update continuously as new queries stream in. A query that goes viral today must surface as a suggestion within minutes, not days. Fourth, the system must support personalization. Suggestions for assigned user should factor in their past searches, location, language, and device context. Fifth, the system must support multi-language and locale-aware completions, handling Unicode, right-to-left scripts, and locale-specific trending. These 5 capabilities define the user-facing contract of a production-grade Typeahead system. Now the non-functional requirements. Latency is the defining constraint. The 99th percentile end-to-end response time must be under 100 milliseconds, including network round-trip. For a global product, this means serving from edge nodes co-located near users. Availability must be 5 nines, 99.999%. Because a broken search box is the most visible failure a product can have. The system must scale to hundreds of thousands of queries per second at peak, with horizontal scaling that does not require reindexing the entire tree. The index must support near real-time updates. Trending queries should propagate within minutes. Storage must be efficient. A raw tree for billions of queries consumes terabytes, so compression and pruning are mandatory. Finally, the system must be fault-tolerant. A node failure must not degrade suggestion quality for users being served by healthy replicas. Here is the high-level system architecture. On the left, clients send prefix queries through a global load balancer and CDN edge layer. Edge nodes serve cache suggestions for the most frequent prefixes directly, with 0 backend calls. Cache misses route to the Typeahead query service, a stateless fleet that looks up the prefix in a distributed in-memory tree store, think Redis cluster or a custom shard-aware tree service. In parallel, a data ingestion pipeline collects raw search queries from the search service, processes them through Kafka, and feeds a MapReduce or Spark aggregation job that recomputes query frequency counts. The Tree Builder service takes the aggregated counts, builds or incrementally updates the tree, and publishes new tree snapshots to the tree store. A personalization service enriches suggestions with user-specific signals before the final ranked list is returned to the client. The key metrics to memorize cold. P99 suggestion latency must be under 100 milliseconds measured at the client. Cache hit rate on the edge CDN should exceed 90%, because uncached prefix lookups are expensive. Index freshness measures how quickly a newly trending query surfaces as a suggestion. Target under 5 minutes for trending topics. Suggestion click-through rate measures how often users actually select a suggested query versus typing their own, which is the primary product health metric. Prefix coverage measures the fraction of real user queries for which the system returns at least one suggestion. Index size and memory footprint per shard determine horizontal scaling costs. And query ingestion throughput, measured in events per second, determines whether the tree update pipeline can keep up with search volume. Let's trace the end-to-end user journey. A user opens the YouTube search bar and types the letter A. The browser fires an autocomplete request with prefix equals A. The request hits a CDN edge node where the top suggestions for the letter A, already cached, are returned in under 10 milliseconds without touching the back end. The user continues typing and enters ARTI. This longer prefix misses the edge cache and routes to the Typeahead query service. The service hashes the prefix to the correct tree shard, fetches the top 10 candidates, calls the personalization service to re-rank based on the user's watch history and language, and returns 5 ranked suggestions in 40 milliseconds total. The user selects the suggestion for artificial intelligence, the search executes, and that query event is streamed to Kafka, aggregated, and used to update the query frequency count, closing the feedback loop that keeps the index fresh. The core models and algorithms. The tree or prefix tree is the foundational data structure. Each node represents a character, and the path from root to a node spells a prefix. Each node stores the top k query candidates for that prefix, precomputed and sorted by score, so a lookup is O of the prefix length, not O of the vocabulary size. Because a raw tree is memory-intensive, production systems use a compressed tree, also called a Patricia tree or radix tree, where chains of single-child nodes are collapsed into a single edge. Ranking combines a query frequency score, a recency or trending boost computed from time-windowed aggregation, and a personalization score from collaborative filtering or embedding similarity. Consistent hashing distributes tree shards across nodes, so that adding capacity does not require full reindexing. The tree is rebuilt periodically from a full frequency snapshot and patched incrementally between rebuilds. Now the low-level design deep dive. The tree is stored as a serialized data structure in shared memory on each serving node, enabling zero-copy reads. Each tree node contains the compressed prefix string, a pointer list to child nodes, and a fixed-size sorted array of the top k query score pairs. Because storing the top k list at every node would be prohibitive, the system uses a lazy propagation strategy. Top k lists are only materialized at nodes above a configurable depth threshold, typically 3 characters, where query volume justifies the memory cost. Below that threshold, the service performs a bounded depth-first traversal to collect candidates on the fly. The tree builder publishes immutable snapshots to an object store, such as Amazon S3 or Google Cloud Storage, and serving nodes hot swap to the new snapshot with zero downtime using a read-write lock. Incremental updates between rebuilds are applied as a delta patch via a small update log replicated through Kafka. The personalization service maintains a low-latency user feature store, Redis or a dedicated embedding lookup service, so the re-ranking step adds at most 10 milliseconds to the total response. Key takeaways for your interview. First, the core data structure is a compressed tree with precomputed top k lists per node. Know the memory trade-off between storing top k at every node versus lazy traversal below a depth threshold. Second, the architecture separates the hot read path CDN edge cache stateless query service in memory tree store from the cold write path Kafka ingestion batch aggregation tree builder, and you must explain both. Third, caching is the single biggest latency lever. Edge caching of frequent prefixes eliminates the vast majority of backend load. Fourth, near real-time index updates require an incremental patch mechanism on top of periodic full tree rebuilds, and you should explain why full rebuilds alone are insufficient for trending queries. Fifth, personalization adds a re-ranking layer that must not blow your latency budget, so it runs in parallel and is bounded by a hard timeout. If you walk through these 5 points clearly and discuss the trade-offs at each layer, you will signal strong senior-level design thinking. That's it for Typeahead and Autocomplete. If this helped you, please like and subscribe, and I will see you in the next one at Cloud Wizard. And that's a wrap on Typeahead and Autocomplete. We covered the full picture, from the compressed tree and Topk precomputation through edge caching, Kafka ingestion, Spark aggregation, tree builder snapshots, personalization re-ranking, and the low-level schema and serving pipeline. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design deep dive. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.